This video is about correlation and regression analysis using R. Correlation is defined as measuring and quantifying the strength and direction of a relationship between two or more variables. And then the next one will be regression analysis. In regression analysis, we model the relationship between a dependent variable and one or more independent variables. And the objective of regression analysis is to understand how changes in independent variable are reflected in dependent variable. Okay, here we have RStudio, and the first one I'll be doing correlation test. And in order to import a file, I will use this command. That's my file. And this is the name of the object. You can choose any name of your choice and then read.csv and then file.choose and then parentheses open close and then another parenthesis. So this is the command that we use to open a CSV file and to import it into RStudio. Once it's imported, then the next step would be to attach it. And for that purpose, I will use this command that's called attach my file one. That's the name of the object. This is the name of the object, and I'm going to attach it. And in order to run it, you can either click on this one, run, or you can press Control Enter. I will press Control Enter. Okay, let's say the data that I'm going to use for this one is called as income happiness. And I want to see what is in this data. So for that purpose, I will use this command that's called as view my file one. And it has opened this file. It shows that in this data, we have these variable income and happiness. Okay. And it shows that 1 to 16 of 498 entries. So it's a really big data. 498 entries, and there are 3 columns, but there are only 2 columns of our interest. One is income and other is happiness. So basically, in this data set, we want to know what is the correlation between income and happiness. In other words, we want to ascertain if income increases, does it also increases level of happiness or not? Although I do not intend to imply any causation. So this is our data, the structure of our data, and let's run it. And in order to run it, I will use this command that's called as core.test, cor.test, and then the name of these variables, income and happiness. So if I run this command, given us this correlation, in these results, there are a number of things, but the most important thing is this correlation results. That's 0.8656. In other words, the correlation between income and happiness is 86.56%. That's the most important thing here. Then the next thing is p-value. I will be explaining p-value very soon, but in general, this is related to hypothesis testing. We make hypothesis, and our default hypothesis is that there is no relationship between income and happiness. That's called as null hypothesis. That's a default one. So RStudio has automatically developed this one that, okay, if your null hypothesis is that there is no correlation between income and happiness, then alternative hypothesis would be that true correlation is not equal to 0, which means there is some correlation between them. And the p-value, whenever p-value is less than 5%, then we reject the null hypothesis. And the null hypothesis again was that there is no relationship between income and happiness level. Because this p-value is less than 5%, so we would say that we have significant confidence that these findings, they can be generalized. Now, this is scientific notation. It's a very, very small value. It says 2.2 and 10 raised to power negative 16, which means that we need to move this decimal to 16 places on the left. So one digit is already there. We need to add 15 more digits. So we will place here 15 zeros before this 2. So that will be a very, very small number. It will be 0.000, and then you write there 15 zeros and then 2. So that will be very small value of p, which means we have confidence that this pattern or this relationship is not happening just by chance, and that we can also observe this phenomena in the broader population. Now let's make a plot of this one, and for making plot, I will use this command that's called as plot. I will be making a scatter plot. Let me write here scatter plot. So scatter plot between income and happiness, and for that I will use this command plot income and happiness. This is the minimum command. And then other things, they are auxiliary, they are just cosmetic. So color is equal to green. You can also choose any color from HTML color code website, and this is fill. If you don't use it, it will just give you empty circles. But if you use this PCH is equal to 16, then those circles will be filled. So let's say if I run this one, and let me expand this one here. So if I run this command, it gives us this one. So as we can see here, there appears to be a very strong correlation between income and happiness. Now, we have to add here many things. For instance, we have to add here title, and for that I will use main is equal to. But this is the minimum command to make a scatter plot. Then next thing is that sometime we want to add here a line. We want to add here a regression line. We want to see that how this relationship unfolds. And for that purpose, I will use this command that's called as AB line. LM. LM stands for linear model. And then dependent variable, it should come first, followed by tilde sign, and then income, that's independent variable, and the name of data. The name of data is my file one. It's the same one that I had created here. You can see the object that I created that's storing my data. It has developed this line. So this line is sometimes helpful to understand the relationship between two variables. You can also practice correlation using cars data that's built in R. But now I will move to regression analysis. And for that purpose, I will use a data that's called as heart regression. And again, this is data that's not built in R, so I need to import it. And for that purpose, I will use this command. It's the same command that we use to import data, external data into R. And myreg, that is just the name of the object where I can choose any name, is equal to read.csv file.choose and then parentheses. And if I run this command, it will open a window and it will ask me, okay, where is your file? And I will choose from there because I have already uploaded it here, so I don't need to. Then in the next step, I will attach that file. The name of that file is myreg. That's an abbreviation for my regression. And then I will run this command. This is the command that is used for regression analysis. Again, I create an object and the name of object is my regression is equal to LM, which means linear model, and then heart disease, biking, and smoking. But before we go that, let's see what is in this data. What type of variables are in this data? And for that purpose, I will use this command that's view my reg, which means I want to see what is in this file. And if I run this command, it shows that in this data, we have three variables. One is biking, other is smoking, and other is propensity or chances of heart diseases. So there are four columns. And again, as you can see here, showing 1, 2, 3 or 498 entries, again, which means it's a big data and there are four columns, but columns of our interest are these three: biking, smoking, and heart disease. Now here we need to figure out which one of them is dependent variable and which of them are independent variable. Pause this video for a few seconds and figure out which one of these is dependent and which are independent variables. biking and smoking, they are independent variables. And heart disease, it depends on biking or smoking, which means, for instance, our common knowledge tells us that if someone is doing biking, they would be healthy, so their heart disease would be less. So heart diseases depends upon biking. So therefore, heart disease is a dependent variable because it depends upon biking. So it's a dependent variable, and biking is an independent variable. Similarly, about smoking, smoking is an independent variable. And we know that heart diseases, our common knowledge tells us that heart diseases, they depend upon smoking. Our common understanding is that if someone smokes more, there might be a possibility of having heart diseases. So therefore, we say biking and smoking, they are independent variables, and heart disease is a dependent variable. Now, in regression analysis, we want to model this thing and we want to build an equation and we want to understand that how do these two variables, biking and smoking, they predict the propensity of heart disease. And we want to make an equation whereby we could predict if someone is biking, let's say, 10 miles every day, or if someone just smokes one cigarette a day, then what would happen to heart disease? Or if someone is biking 5 miles a day and someone doesn't smoke at all, then how it would affect heart disease? So we want to model this relationship. Okay, so using this one view myreg, it shows that we have these variables. Now, then I will run this command for regression analysis. Again, it says my regression. My regression, that's the name of the object that I created. It is storing all the information. LM stands for linear model heart disease. That's a dependent variable. And then followed by tilde sign. And then independent variable are separated by a plus sign. So this biking and then plus sign and then smoking. Okay, and when I run it, and then in the next step, I want to see, okay, the regression has been run, and I want to see what is there in this my regression, in the object that I created. So I will use this command that's called summary, my regression. And if I run it, it gives me these results. Now, again, and there are many, many things here, but let's discuss the key things first. The most important thing here is this one, that's adjusted R square, which is 0.9795. In other words, this is 97.95%. So which means that's a relationship between dependent variables and independent variable. So this is a very strong relationship. It means it's a very good model. Then another piece of information that we will use is intercept. Intercept is 14.98, which means that when x-axis is 0, then the value of y will be 14.98, or if you round it off, it will be about 15. And the next thing is biking. This is the slope of biking. It shows that for independent variable, when you move 1 degree on x-axis, then the corresponding change on the y-axis is negative 0.200133. And for smoking, this is the slope, which means if we move on x-axis by 1 unit, the corresponding increase is 0.178334. And you can see here that there's a difference. For biking, it's negative, and for smoking, the slope is positive, which means that smoking has a positive effect and biking has a negative effect, an inverse effect. If someone does more biking, they are likely to have less chances of heart disease. And then another thing is p-value. So this is p-value. Again, this p-value is very, very small. It is 2.2 and 10 raised to power negative 16, which means that we need to move this decimal, that's between 2 and 2, to 16 digits towards left. So 1 digit is already there. We need to add 15 zeros here. So 0.0000 15 times and then 2, that is the p-value. Again, that p-value is very, very small, which means that we can have more confidence. Now, I will explain this a little bit more, this p-value. But for that, let me clear this one. Okay, so for this one, I'll be using a data that's called cars. So this is a data that's built in R, which means you don't have to import it. So let's say if I just run it, if I type here cars and I run it, so this data is there. And if you see, this data has two variables, one is speed and distance. So essentially it means speed is one variable and distance to stop the car is another variable. Now pause the video for 1 minute and figure out which one of these two is a dependent variable and which one is independent variable. Okay, so speed would be independent variable and distance to stop the car, that depends on speed. So that would be a dependent variable. So distance will be a dependent variable and speed is independent variable. Because if you are going at a very high speed, then distance to stop the car would also increase accordingly. So this distance to stop the car, it depends on speed. So therefore, distance is a dependent variable. Okay, in the next step, I will attach it and let's draw a plot, which means a scatter plot between these two variables, speed and distance to stop. If I run it, it gives me this plot. And again, we can add more information here. We can add here color and then we can fill it by using PCH is equal to 16. Okay, now in this one, I want to add here a line, a regression line. And for that, I'll be using the same command, that's AB line LM linear model distance, that's the dependent variable, it will come first, and then tilde sign speed, and then the name of data is equal to cars. So as you can see here, it has added here a line. Okay, now if I conduct a regression analysis of this one, let's say I create an object and the name of object is myreg3. Again, it's my choice, I can use anything, but for here I don't have choice. So for one, I will use this command lm linear model distance, that is a dependent variable, and speed is independent variable, and they're separated by tilde sign. And if I run it, it has run it, and then in the next step, I want to see what is in there. So I will use this summary myreg3, and it says that in this one, our adjusted R square, the relationship is 0.6438. P-value is 1.4910 raised to power negative 12, which again is a very, very small value, which means that we have more confidence that we can observe this phenomena in broader population also. And then this is slope, that's negative 16.5791, which means when speed is 0, then this line, it will be touching y-axis at negative 16.57. And then slope is 3.93, which means every time you move here, the corresponding change in distance to stop would increase by 3.9. So that's a slope. Now, about this p-value, the idea of this p-value is that we describe it in two ways. First of all, technically. So technically, we say that just imagine that this slope is 0. And if we collect data and we conduct this regression analysis, what is the probability that this one is just by chance or by error or due to some problem in our data? So that probability, as you can see, is very, very small. P stands for probability value. So therefore, we would say that we have high confidence that these results are sound. And it also means generalizability, which means we can generalize these results to broader population. Now, this is an important point. You see that in this data, we have 50 observations. P-value means that although the relationship between speed and distance to stop car is about 64.38%. But we can also say that the same phenomena will also be observed in the broader population. In other words, although in this test we concluded this thing based on just 50 observations, that is our sample. But how confident we are that this effect or this relationship would also hold in broader population, not just your sample that was 50 observation, but also in the population. And when this p-value is small, we can say that we are confident that this effect or this phenomena will also be observed in the broader population, which means generalization. Okay, let's discuss one last example. And in order to clean this console, you need to press Ctrl L. And to clear this one, click on this broom. Now, the last data is about crime-related data. Now, again, this data is not in R, so I need to import it. I will use this command, that's myfile2. Myfile2 is the name of the object that I choose. And then read.csv file.choose. Here, I do not have any discretion. I have to use this command. I cannot make any change here. Although I can change, I can choose a name of my choice for this one. Okay, once I run this command, it will open a new window, and then I will go to my specific folder and import that data. And the next step is I need to attach it. So attach my file. Okay, it has been attached. And now I want to see what is there in that data. So let me see. Now here is the structure of this data. It says we have these variable, and one of the variable is aggravated assault. Second is bachelor's degree. Next variable is police expenditure per capita. Next variable is population in millions, and then population density per square mile. And the last one is unemployment rate. Now, I know it's a little bit tricky, but I want you to stop this for a few moments and decide which one of these is a dependent variable and which variables are independent variable. Aggravated assault, or in other words, crime rate, that is a dependent variable. Because in this data, we want to determine that how crime rate is affected by the education of people. That will be determined by bachelor's degree. So crime or aggravated assault will be a dependent variable that depends on these five independent variable. And the first independent variable is bachelor's degree. Then police expenditure per capita, that is another independent variable, because crime rate also depends on to what extent police have resources. Population in millions is another independent variable. And then population density, that's person per square miles, that is another independent variable that will determine how much crime rate happens. And the last thing is unemployment rate, which is perhaps the most important variable. We know that if unemployment rate is high, perhaps there might be a higher probability of having crime rate. Although it is just an assumption, the true thing, the facts will come when we analyze this data. But this is the structure of the data. This is dependent variable and these are independent variables. Okay, now we want to see scientifically and objectively how this model can be made, or how these independent variables would determine dependent variables. And again, I'll be using the same format, which is, I would say, my regression 2. My regression 2 is the name of the object where you can choose any name is equal to LM, that's linear model. And then dependent variable will come first. So aggravated assault, or that's the dependent variable, so it will come first, and then followed by this tilde sign, and all other independent variables, they will come afterward and they will be added. They will be separated by plus sign. So that's the whole equation command for regression analysis. Okay, if I run this one, it has been run, as you can see here. It in the console it appears in blue color, which means the command has been run. Now I want to see summary of my regression to, okay, what is there, what are the results? And if I run it, it gives us these results. And again, the very first thing, the most important thing, adjusted R square. Adjusted R square is relatively less. That's 25.08, which means that this model is not a very strong model, not a strong model, not even a moderate model, but a rather weak model. In other words, the extent to which these predictors or independent variable, they determine dependent variable, that model is relatively weak, but p-value is very low. This one, adjusted R square, it shows that this model is not a very strong model. I mean, there is a relationship, we can say, but that's a very weak type of a relationship. But p-value indicates that because p-value is less than 5%, a 5% would be 0.05. Because this p-value is less than 5%, it means that we are confident that this phenomena that we have seen here, the phenomena is this one, this relationship, it will also hold in broader population. If we go beyond this sample, can we also observe this phenomena in the broader population? Yes, we can do that, which means it didn't happen just by error. That gives us confidence in our results about their generalizability, that we can observe this phenomena in the broader population as well, not just only in the sample. And then the next thing would be these intercepts. So intercept is 57.955, which means that when x variable is 0, then y will be 57. And bachelor's degree, this is a negative slope. There are more people who are educated, crime rate would be lower. So although it's a little bit weak, a slope is very small, but it's negative. So which means that if you increase number of people with bachelor degree, then crime rate would be lower, although very small slope. And then police expenditure per capita, it says that if you increase this one, then the slope is 0.46. Again, it's not very strong, but it is positive. And then population density is also has a very small value of slope, and population in million, that has a relatively high value of slope, and similarly unemployment rate. But in case of a population in million, which appears to have high value of slope, that's very informative here. Now, the last step here is to make a regression equation. This is how we make a regression equation. The regression equation will be, here I have made a regression equation that was for the other one for heart data. And in that case, it was heart disease, which was a dependent variable is equal to slope. And then intercept, this was intercept, and then slope, and multiplied by biking, which means if someone walks 10 miles, you will substitute biking by 10. Then plus 0.178334, that is the slope of smoking. And here is smoking, which means if a person smokes 5 cigarettes per day, then this smoking will be substituted by 5, and that will give you propensity or the chances of heart disease. Now, in the same way, we can also make an equation for this one, and that equation will be a crime rate or aggravated assault is equal to intercept, and we know intercept in this case was 57.95. This is 57 point. So I will just copy this one is equal to intercept, slope of next variable, and next variable is bachelor's degree. So I will just copy this one multiplied by a name of variable, that's bachelor's degree. And then next one is variable, that's police expenditure per capita, and that's 0.467 multiplied by police expenditure. And this variable is really important because a few years ago, there was a movement that was going on in some East Coast states that was about to defund the police. So this type of data is really informative to make decisions or to test those type of claims, although we don't have much data here. And then the next one is population density 0.008565 and multiplied by population density. Second last one is population in millions, and its slope is 25.23 plus 25.2377 multiplied by population in millions. And the last one is unemployment rate, and its slope is 16.55 plus multiplied by unemployment rate. Here I can write here crime rate is equal to, so this is our equation. And let me add here this hash sign, which means that it's not a command, it's just an equation. So for policy making, whenever you want to see what would be the impact, I mean, if you want to convince someone that if you want to prevent crime rate, then what should you do? Then this is the equation that can tell you what you should do. So over here, for instance, in this case, first of all, we see that unfortunately, it's not a very good model, which means these variables, they are not a very good predictor of our dependent variable, which is crime rate. So in this case, what would you do? First of all, per se, it appears that they are not very good predictor. It's not a good model. Second thing, if you strongly believe that they are very good predictor, they should determine, because that's very intuitive, it's logical, it makes sense. Then maybe you can collect more data, because right now we don't have much data, and you need to collect more data. And once you have more data, then maybe we might have a different picture, or maybe the same picture remains there. But in any case, having more data is always desirable. That's one thing. And next thing, this p-value, that was very informative. That was about generalizability of these results. And then it also tells us about the slope. And again, here are p-values. These p-values, they have exactly the same interpretation, same meaning as I'm discussing here, but these are for individual variable. So for instance, let's say if we say that police expenditure, police expenditure, it has relatively high slope, and the value is also equal to somewhat very close to 0.05, although it's a little bit higher, but relatively close to that. So which means that police expenditure, it appears to have some effect on crime rate.